Okay, so in today's lesson, guys, we're going to go over a vector test summary. So if you're away today, a bad lesson to be away, try not to get sick. So we'll go through the sheet, we'll talk about what the test is going to include, and then we'll go through the review questions together. So it's a big unit, right? We've done chapter 5 and 6. So at this stage, our test is scheduled for Monday of week 10. So that's this time next week. And we can shift that a little bit depending on how we're going with revision and so forth. But it'll go for the whole double, 60 marks. You get your calculator. You're allowed to bring 1 page of handwritten notes. So that's your cheat sheet. And you can bring the formula sheet if you would like. That's up to you. Bring your own approved formula sheet via SACE. So the content is everything from chapter 5 and 6. The good news is chapter 5, most of chapter 5, I would say all the way up to 5H, okay, so 5A through to G, very basic skills with vectors that we learnt in 2 dimensions in year 11 and that really correlate and cross, they're skills that are applicable across both to 3 dimensions. And so then we've spent the bulk of our time going through 5H, 5I, and then chapter 6. Okay, so I've got a skills checklist there, and so I've tried to condense it down into, what have we got? We've got 6 basic skills there. So we've got perform operations with vectors manually and using technology. Okay, so just operation with vectors, and then I've tried to come up with a list of what this includes. So adding and subtracting vectors, dot product between vectors, cross product between vectors, magnitude of a vector, finding a vector between 2 points, finding the angles between 2 vectors, finding the area of triangles using vector techniques, and the area of a parallelogram. So all of that, pretty basic skills, and we will have a recap of most of those today. All right, then we've got describe the equations of lines in 3-dimensional space in vector, parametric, and Cartesian form. So familiar with the 3 techniques we can use to describe a line. And then we've just got, generally speaking, solving problems involving lines in 3D space. So this includes stuff like distance between skew lines, angles between lines, points of intersection between a line and a line, points of intersection between a line and a plane, and so forth. And then we have constant velocity problems. Then the next 2, describe the equation of a plane and then solve problems involving planes in 3 dimensions, such as planes intersecting with lines and planes intersecting with other planes, up to 3 planes coexisting in a system. How do those 3 planes interact? Solve problems involving vector proof. So we did vector proof in chapter 5, 5H. We have vector proofs there. That's where we touched on the triangle inequality. And we will have an opportunity to address them again today. Lots of exams in the past, they definitely have vector proof questions. So it's a skill that I think we sort of spent a lesson or 2 on, but we're going to have to definitely recap it today. All right, as far as the revision resources go, you've got tests from 2017 through to 2023. So I've given you guys 2020 on to 2023. So I've given you 4 tests. There's another 3. I'm very happy to print them for you. We've got the review set questions, so that's in the back of the textbook, chapter 5 and chapter 6, the review set's there. All of those questions are relevant. And then the vector exam questions booklet. So what I was saying at the start of the lesson, I don't expect you to get all of that done. It'd be fantastic if you do, but this is questions that I've plucked from previous exams and assembled into a booklet. You'll find work solutions on the OneDrive, and this is really indicative of how the exam tends to ask vector-based questions. And so you don't have to get it all done now. We can even use it when we're doing exam revision later this year. All right, but I'll give it to you now. You've got it, and I recommend doing as much of it as you can in preparation for the test regardless. Okay, excellent. So that's our revision resources sort of summarised down the bottom there. Let's get into the review together. So, how cool is this question over leaf? So I'll get you guys to write down answers as we're going through it. But we've got question 1, and it goes from A through to H. And so what I've done is I've invented 3 points in space, and then I've just said, let's basically do everything we've done with vectors with these 3 points. So a good opportunity for us to recap it. So we have point A, it's not the marker I had before. point A, we have 3, 2, 0. Point B, we have -1, 2, and -4. And then for C, we have 0, 1, 2. Okay, they're the 3 points that we have in space. 3, 2, 0, -1, 2, -4, 0, 1, 2. 0, -1, 2. Make sure we get it right. Good. Okay, part A. Find vectors AB and vector AC. So the vector from A to B is the coordinates of B, take the coordinates of A. So we'll have -4, 0, -4. And the vector from A to C is going to be the coordinates of C, take the coordinates of A. So we'll have -3, -1, take 2 is -3, and 2. So we have vectors A, B, and AC. We've answered part A. Part B, find the area of triangle ABC. So this is from exercise 6A. If we have two vectors comprising a triangle, like let's call them P and Q, then the area of this triangle is half the modulus of the cross product of P and Q. Alright, so that means the area of our triangle, our circumstance, we've got AB, like here's point A, here's point B, here's point C. We've got AB and AC. And so the area of this triangle then is going to be half the modulus of AB cross AC. Now, we don't get any points for really working out for the cross product. So whatever's the fastest way for you to do it, whether it be in your calculator or doing it manually. So let's pull our calculators out and we'll use the program that we've been given. So program AX cross B, and first vector is AB, so I'm doing this one. -4, 0, -4, and then we have -3, -3, 2. Okay, so we're going to have it's half times the modulus of this vector, which is -12, 20, and 12. And the beauty of that is that, of this program as well, is that it even does tell you the modulus of the vector, doesn't it? The length of it is the square root of 688. So that's the area of this triangle. All right.
Unit squared.
Say again.
Unit squared.
Units squared for area. Very good. Excellent. Okay, so that's part A, part B done. Part C, prove that AB is not perpendicular to AC. Prove that this angle is not 90 degrees. So the point I want to highlight here, whenever we're talking about perpendicularity, we're talking about dot product. They're perpendicular, so perpendicular if AB dot AC equals 0. Okay? If the dot product of them is equal to 0, they will be perpendicular. When we do the dot product of AB and AC, -4, 0, -4, dot, -3, -3, 2. We're going to get +12 plus 0, take 8. We get +4. +4 is not 0, therefore they are not perpendicular. Okay. C then goes on to say, alright, well, find the angle between AB and AC. If they're not perpendicular, find that angle in here. So we're talking about angles between vectors. This is in chapter 5, so you can look at your notes or look at your textbook. So 5G we're looking at, and we'll just come up with a nice formula there for angles between vectors. All right, cos theta is A dot B. So that's the same as this part. Cos theta is A dot B on mod A on B. Okay, so the angle between these vectors then is, we know the dot product is 4, and then we're just going to have the modulus of AB times the modulus of AC. The modulus of AB is going to be 4 squared plus 0 squared plus 4 squared. That's 16 plus 16. And the modulus of AC will have 9, 18, 22. Alright, so theta is going to be the inverse cos of this. We'll evaluate that. All right, am I going too fast? Are we okay? Yep. Jack, feel good?
A little.
Yeah, let me know. It's because I write messy and you write much neater than me.
Yeah, I'm good now.
Cool. And I'll evaluate that. And I've got 1.419, 1.42 radians. Very good. Okay, that is part C. All right, part D, I like this question. Find the coordinates of D that lies along AC such that the area of triangle ABD is twice the area of triangle ABC. So think back to our triangle here. We've got the coordinates D that lies along the line AC. So this is going to be D. And it's here such that the area of this triangle, ABD, is twice the area of triangle ABC. Okay. So, because D lies along AC, the relationship we're going to draw out is that AD, even let's write it like this, AD is equal to K times AC. It's equal to some scalar multiplied by vector AC. Alright, that this vector is some multiple of this vector. Okay, so this is part D. Now, we're told the area of this triangle is twice the area of this triangle. So that means the area of triangle ABD has an area that's equal to not half root 688, but root 688. It's twice that area. If we multiply this area by 2, we're just left with the root 68. 68, 8. Okay, so that's the area of the triangle. Now the area of the triangle, right, is going to be half AB cross AD modulus. Okay, and this is where we come in with a little bit of operation. Well, we know that AD is K times AC. The other thing I'm going to do here is multiply both sides by 2. Alright, so I can get AB cross K times AC. I'm just performing that substitution. And over here we'll have 2 root 688. And then one of the properties of cross product is that this is equal to the modulus of K times the modulus of AB cross AC. Now we know AB cross AC, we've already evaluated that, we did that up here. AB cross, the modulus of AB cross AC is root 688. And so we've got K is 2. Okay, the value of K is 2. So, I might continue just working here. I think we'll have enough room. So what this is going to allow us to do is find vector AD. Vector AD is equal to 2 times vector AC. So that's going to be, I'm just going to do it in one step. 2 times vector AC, which is minus 6 minus 6, 4. Okay, that is vector AD. That's the vector from A to D. All right, so we're getting there. Remember, what have we done? We've found the vector AD. We're trying to find the coordinates of D. What are these coordinates such that this area is equal to this area, such that the area of triangle ABD is double? Okay, so if we want the coordinates of D, what we want then is we want vector OD, the vector from O to D. And vector OD is going to be equal to OA plus AD. Alright, we've already got vector AD, and we know vector OA is just the coordinates of A expressed as a vector. So that's 3, 2, 0. Plus, and then vector AD, minus 6, minus 6, 4. Okay. add those together, it gives us vector OD, which is the coordinates of D. So we'll have -3, -4, 4. So therefore D -3, -4. Okay, so now if you go ahead and find, you know, if you do the cross product of half AB and AD, you'll see we get an area of 688, root 688. Okay, so that's a little bit tricky, that one. It's a bit more drawn out there, isn't it? So what did we do? Okay, I'll point out a few things. We first identified this relationship. Because D lies along the line AC, it's a scalar multiple relationship. AD equals K times AC, some constant. We don't know what it is. Okay, we do know the area of triangle ABD is going to be this because it's double triangle ABC. So we wrote that down. Then we've manipulated this expression. We know AD is KAC. We know one of the properties of cross product is that we can pull that scalar constant out the front. We've identified the value of K. Once we've found K, we can find vector AD. Once we've found vector AD, we can go on to find vector OD, which gives us the coordinates of D. All right, so remember that, Jack? That's okay? Yep, Jeff, all right with that? Excellent. Okay, let's have a look at E. Find the equation of the plane that is composed of points A, B, and C. Okay, so I'm going to clear some space here. So, points A, B, and C, if we want the plane that's composing them, well, we want vector AB cross AC. That's going to give us the normal. All right, AB cross AC gives you a direction vector that is perpendicular to both. We've done AB cross AC, it's this one here, which means the direction of our plane for part E, the direction vector of our plane is 12x plus 20y plus 12z, being equal to our constant D. And we can substitute in any coordinate to determine the value of D, right? So we've got coordinate of A is 320, let's put A in, 12 times 3 plus 20 times 2.
Wouldn't it be negative 12x?
Yes. Yes. Is that negative 12, is it?
No. Is it? No.
No. It might, I reckon one of them is negative. I think you're right. Let's get it right. What did you have, Jeff? Yes. I'm just going to type in AB cross AC again. I reckon one of them was supposed to be negative. Which one did you have? This one?
The first one.
First one. I'll trust you. All right, let's put that as negative. So that's negative 12 plus 40. And then plus, this is 0. The z coordinate is 0. Equation of the plane, point A, 320. Cool. All right, so we've got minus 36 plus 40. So this gives us D is 4. So therefore the equation of the plane, minus 12x plus 20y plus 12z is positive 4. Okay. Part E, find the equation of the plane, done. Okay. Part F, find the shortest distance from the coordinate 202 to the plane ABC. Okay, so there's a formula that we can use here for this, but I'll just talk about the process. We won't go through the process, I'll just talk about it, and we'll use the formula in the end. Okay, so we have a plane in space. All right, this is the equation of the plane, and we have some point sitting somewhere above the plane. Well, the shortest distance from this point to the plane is going to be when it's perpendicular. All right, so one way we could think about this is, I know the direction of this line, it's here, minus 12, 20, and 12. I know that it has to pass through this point, 202. And so all of a sudden you have the vector equation of the plane. We have a coordinate plus a direction. And then we go, all right, now when does this line satisfy the equation of the plane? So we would substitute the vector line into the equation of the plane. We obtain some value of t. We put t back into the equation of the line. It gives us these coordinates. Okay, coordinates of the foot of the perpendicular, and then we just find the distance between two coordinates using distance points. Okay, that's a long drawn out way of doing it, but we do have a formula right at the end of chapter 6. So if I flick you there, in our notes and in our textbook, 6H, and we introduced planes. Yeah, so it's in our notes book, but it's not explicitly shown in the textbook. This is the formula here. It pops up in one of the questions in the textbook. It says A times x1 plus b times y1 plus c times z1 plus d, the modulus of that on top of the square root of a squared plus b squared plus c squared. Okay. Where A, B, C, and D is the direction of the normal, or the equation of the normal, x1, y1, z1 is the coordinates. Okay, so I'm just going to plug those into this formula. We want to know what's the shortest distance from this point to this plane. So we have minus 12, so we have the modulus of minus 12 times 2, and then plus 20 times 0, plus 12 times 2. And then at the moment, right, D is over here. So if we're going to move D to be on this side, we're going to have D is minus 4. Okay, when we move it over. So that's modulus. And then on top of the square root, the modulus of the direction vector of the normal. Okay, what are we going to have? Minus 24 minus 28 plus 24 gives us modulus of minus 4 on, and then this, what was that, 688? 144, 144, yep, plus 400. And so we'll evaluate that. 4 on top of root 688. And simplify, like in simplest third form, root 43 on 43, or to 3 significant figures. It's a distance 0.152 units. Very good. Okay, so you can do the long process that I expressed. It's a very intuitive process and it solves a lot of vector problems, or we can just smash it into the formula to get the answer. Both of those are appropriate ways of doing it. Probably the formula's a fair bit faster. Okay, on to G. All right, we're given the equation of a line in Cartesian form. Now I've intentionally done Cartesian because I want to draw out the relationship with Cartesian to vector and parametric form. So we have, this is for part G. The line is x on top of 4 equals y take 3 on top of 2 equals 1 take z. Okay, so the first thing we do is that we equate each part. If we're converting it to vector form or parametric form, we just start by equating each term to our parameter. So I'm going to go x on 4 equals t. This gives me x is equal to 4t. All right, we have y take 3 on top of 2 equals t, times both sides by 2 first, and then add 3, so we have y equals 3 plus 2t, and we have 1 take z equals t, so we can just swap the z and the t, we'll have z equals 1 take t. Okay, so we're just equating to t and solving through for x, y, and z. So here we have the parametric form of the line. If we were to express it in vector form, well, we want a coordinate plus t multiplied by a direction vector. All right, so the coordinate is going to be 0, 3, 1, and the direction is 4, 2, minus 1. Okay, so drawing out there the ways that we can present the equation of a line, right? Now, our question is, when does this line meet this plane? The line is going to meet the plane when it satisfies the equation of the plane. So we're going to substitute this equation of the line into this equation of the plane. So we have, minus 12 multiplied by our x, and then we have plus 20 multiplied by our y, and then we have plus 12 multiplied by our z, and that's all equal to 4. We're going to solve through for t, the coordinates of t. So we'll have minus 48t plus 60 plus 40t plus 12, take 12t equals 4. Start to collect. So if I go for the t's first, we're going to have minus 60 plus 40, we'll have minus 20t. We have 60 plus 12 is 72. Take 72 from both sides. And we'll have minus 68. So we'll have t is 68 on 20. And what's that? 34 on 10, 3.4. Okay, so what did we do? We've substituted this line into this plane. We've obtained a value of t. So now we're ready to state the coordinates of where this line meets the plane. And it's just going to be for this value of t. When t is 3.4, we have 4 times 3.4. What's that going to give us? 12, 13.6. And then 3 plus 6.8 will be 9.8. And then 1 take away 3.4 will be minus 2.4. Okay, so the coordinates where this line meets the plane are there. Okay, we got 2 H's. H1. Find the angle that this line makes with plane ABC. So the angle between a line and a plane is 6i. So we have a formula in the textbook and in our notes book, okay, that's where we expressed it. I'll write the formula up here. So we have, here's a plane, here's the line that meets the plane. We're finding this angle in our textbook, it's described as phi, and we have sine of phi equals n dot d on modulus of n modulus of d. Okay, where the line has direction vector d and the plane has normal vector m. Okay, so our line, this is the direction vector of our line, and the direction vector of our plane is our normal is minus 12, 20, and 12. Okay, so we're doing, and I'll put up D here as well, the direction vector of our line, so they're close together, 4, 2, and minus 1. So at the top we have the dot product of these. So minus 48 plus 40, take 12, modulus of that, all on top of. Now we know the modulus of n is root 688, that's popped up a fair bit, and the modulus of this one will be 16, 20, 21. Okay, and we can just evaluate that. So we've got minus 60 plus 40, we've got 20 on top of root 68 times 21, root 688. All right, let's evaluate that. For phi, shift sign, and then 20 on root 688 times 21, 0.1671, 0.167. C. All right, you guys going okay so far? Dealing with these parts? We got one more part to this question. It's a good question because we're really drawing out basically all of the skills involving the algebraic techniques of vectors. Okay. Find the equation of a line parallel to AB but through point minus 4, 4, 4. Okay, so direction vector AB, I've rubbed it out. Who can tell me what was the vector AB? I remember minus 4, 0, 4.
Minus 4, 0, minus 4.
Minus 4, 0, minus 4. Oh, so close. Okay, so that's the direction vector of AB, but it's parallel, so it has the same direction, but it goes through this point, minus 4, 4, 4. So then this line is going to be minus 4, 4, 4, plus some, we'll introduce a new parameter, multiplied by the direction. Okay, so that's going to be the equation of the line for the answer in H subscript 2, because this was H subscript 1. Alright, how do we feel about all those skills? Not bad? Yeah?
Still not fully done writing them all down.
Oh, right, yep. Whereabouts are you? I won't rub it out.
Start of H1.
Oh, right, yep. Alright, well, I'll pause for a sec, I'll let you get it down, and then we'll go through. Alright, so here we are with the vector proof question. And so what we'll do with this one is I just want to draw out one of the properties of vector proof that if you completed the vector proof exercise you would have definitely come across, and that's this one here. We have K1A times plus K2B equals L1A times L2B, and we can equate the coefficients of each vector because they have direction. Okay, basically it's a rule, we're going to use it for this example here. So I've drawn up the image there, and it says, alright, OA and BC are parallel. Okay, OA and BC, these are parallel. And we have BC is 2/3 of OA. So let's write that down. Vector BC is 2/3 of vector OA. And we also have A and B have position vectors A. Okay, the vector from O to A we define as lowercase a, and OB we define as lowercase b. And so this means determine the position vector of E using vector methods. Well, BC we know is 2/3 of A, okay, because it's 2/3 of vector of A. So the way we're going to do this is we're going to go, all right, I'm going to describe vector OE in two ways. I can think of two ways to describe vector OE. The first way is that vector OE is equal to some constant times vector OC. All right, and I can come up with vector OC very easily because the vector from O to C is vector OB plus BC. Okay, OB plus BC. So let's define that. K times, put in brackets, vector OB plus BC. And that's going to be K times B plus 2 on 3 K times A. Okay, so what did I do there? I've said I want to know what is the position vector of E, what is OE? Well, OE is equal to K times OC, and we do know OC. We can see OC based on the relationships that we have already. Okay, then what I'm going to do, I'm going to go, well, what's another way that we can define vector OE, the vector from O to E? And it might be that it's vector OA plus some constant times vector AB. All right, so we might go vector OE is also equal to, so we have one description of it here, we're going to have another description of it here. It's equal to some constant. Instead of K this time, maybe we'll use T. Some constant T multiplied by the vector from A to B. So vector OE is, sorry, let's write it like this. The vector from O to E is going to be OA plus some constant multiplied by vector AB. Okay, so I'll elaborate on what I mean there. want to know the position vector of OE, we can go OA plus some scalar multiple of this vector AB. And we also know what vector AB is, so let's put them in terms of their position vectors. OA is A, and the vector from A to B, the vector from A to B is going to be minus A plus B. Okay, so this gives us then, like, we'll simplify it a little bit. We're going to have A take away TA plus B. And here I'm even going to factorise the A. So we'll have A times 1 take T plus B.
You need TB as well.
TB, good. Yeah, because that T distributes. Okay, so here's where we're going to use that property. So what have we done? We've come up with two different ways of describing vector OE, and because they describe the same position vector, it means they're equal. All right, it means that KB plus 2 on 3 KA equals A times 1 take T plus TB. And because they're equal and because vectors have direction, we can equate each vector. So KB is equal to TB. And so this gives us K equals T. All right, and we also have 2 on 3 KA. All right, 2 on 3 KA is equal to A times 1 take T. Alright, so I equated the B's and now I've equated the A's. And what we're going to do here is we know that K equals T, so we can substitute in either K or T here to solve through for K. We're trying to identify what's the value of K, what's the value of T. So if we solve through, I'm going to put K over here. Okay, we can get rid of A from both sides, like dividing both sides by A. Alright, we're basically, I probably shouldn't have written A because what are we doing? We're equating the coefficients. We're saying the scalar multiples are equal, the vectors are equal, so we can get rid of the vector from both sides. And we're solving for K, right? So if we want to get K by itself, I'm going to add K to both sides. That's going to give me 5 on 3K equals 1. And then I'll multiply both sides by 3 on 5. And we'll get K is 3 on top of 5. We have the value of K, all right? And so now we can use it to answer what is the position vector of OE. I'm going to sub that value of K into this expression here. Therefore, OE, the vector from O to E, is K times B, so 3 on 5 times B, plus, and we have 2 on 3 times 3 on 5, that'll be 6 on 15A. And we can simplify that, but 3 on 5B plus 2 on 5A. Okay? Does that make sense? Yeah? Equating them, and because they have direction, we can just equate the coefficients, we solve through for the K value, and then we substitute it back into our expression. So vector proofs, there will definitely be a vector proof question in the test, and you can probably expect one in the exam. They're pretty common there too.